Hey everyone, and welcome to this explainer. Today, we're taking math right off the textbook page and throwing it out into the real world. Think about the perfect arc of a thrown basketball, or the curve of a satellite dish. It's all quadratic curves. Together, we're going to crack the visual code of these equations. If you've ever stared at a polynomial and wondered what it actually looks like in physical space, well, you're in exactly the right place. So let's dive right in.
Here's our game plan for today. We're going to decode quadratic polynomials, plot the parabola curve, hunt for the zeros, figure out upward or downward curves, and wrap it all up with the ultimate graphing rules. All right, first up, decoding quadratic polynomials.
So what exactly is a quadratic polynomial? Honestly, in simplest terms, it's just a polynomial of degree 2. That means if you look at the equation, the highest power of your variable, which is usually x, is exactly 2. You'll always spot an x squared in there. And let me tell you, that little power of 2, it's the absolute secret sauce here. It's the engine driving the entire shape of our graph, making it totally different from the boring straight lines you get with simple linear equations.
Moving right along to part 2, plotting the parabola curve.
Okay, here's our basic 4-step lab procedure. First, we pick a quadratic equation. Second, we calculate our y values by plugging in different integers for x. Third, we take those calculated pairs and plot them on our graph. And fourth, and hey, please pay close attention to this one, we draw a smooth, freehand curve connecting those points. No rulers allowed, guys. These curves are naturally smooth, and doing it freehand is literally the only way to capture their true mathematical shape.
Let's test this out with our first equation. F of x equals x squared minus 4x plus 3. Notice how the coefficient of x squared here is a positive 1. By plugging in different x values, we start getting our y coordinates. Like when x is 0, y is 3. But when x hits 1, y drops to 0. Do you see the pattern emerging here? As x goes up, y actually drops, hits a low point at -1, and then boom, it climbs right back up. It's this beautiful numerical symmetry. Now, let's swap things up with the second equation. G of x equals negative x squared plus 4x minus 4. See that negative sign at the very front? It actually changes the whole game. Look at the numbers. Our y values rise up to exactly 0 when x is 2, but then they immediately reverse course and drop right back down to -1 and -4. Boom, we've got our second set of points ready to go.
And for our third case, x squared plus 4. Notice how y literally never dips below 4? It just goes up to 5, then to 8. All right, keeping it brisk, we now have 3 totally distinct sets of points ready for the Cartesian plane.
Now, if we were to take all those coordinates we just calculated, plot them, and connect them with those smooth U-shapes, parabolas, we'd notice something super striking. The real question is, why do these 3 curves look so dramatically different from one another? What is the algebra secretly whispering to the geometry here?
Which brings us perfectly to part 3, hunting for the zeros.
Let's break down that first curve, the x squared minus 4x plus 3. If you trace the graph, the curve comes down, crosses the horizontal x-axis at exactly x equals 1, dips down below, and then shoots back up, crossing the axis again at x equals 3. Because it cuts through the x-axis at exactly 2 distinct points, mathematically speaking, we say this polynomial has exactly 2 zeros.
But take a look at our second curve, the negative x squared one. It behaves totally differently. It comes up from the bottom, and it doesn't even cut through the axis. The very tip of it just barely skims the x-axis at a single solitary point, x equals 2. After touching, it turns right back around. Since it only touches at one single spot, this equation has exactly 1 zero.
And that brilliantly illustrates our third scenario. Think back to those points for x squared plus 4. The absolute lowest y value we had was 4. That means this entire U-shape is just floating up there above the x-axis. It never touches it, never crosses it. Because there's 0 intersection with the horizontal axis, this quadratic polynomial has 0 real zeros. None.
So here's the absolute crucial takeaway from all this. A quadratic polynomial can cross the axis twice, it can just graze it once, or it can miss it completely. But no matter what you do, a quadratic equation is never, ever going to have more than 2 zeros. 2 is the absolute maximum limit, period. Okay, moving on to part 4, upward or downward curves. It actually all comes down to the very first number in the equation. If the coefficient of x squared, what math folks usually call a, is a positive number,
the parabola opens upwards. It looks like a big smile, right? Just like our first and third equations. But if that coefficient is negative, like that negative x squared equation we did, the parabola opens downwards, kind of like a frown. That positive or negative sign, it is literally the steering wheel for the direction of the entire curve. And finally, part 5, the ultimate graphing rules.
All right, let's wrap this up with the ultimate graphing takeaways. First, whenever you graph a quadratic polynomial, you're always going to get that smooth, U-shaped curve called a parabola. Second, whether it opens up or down depends entirely on the sign of that x squared coefficient. Third, finding the zeros visually is as easy as spotting the exact x-intercepts. And lastly, thanks to that degree of 2, you're looking at a maximum of 2 zeros. Simple as that.
I want to leave you with this one defining thought from today's explainer. The geometrical meaning of zeros is simply the x-coordinates of the points where the graph intersects the x-axis. Honestly, it's like a magic trick. You're using geometry to solve algebra. So next time you see a basketball arc through the sky or spot a satellite dish on a roof, try to visualize the parabola and its zeros in your mind's eye. Thanks for hanging out with me for this explainer, and keep exploring the amazing world of math.